So it's really just an incredible pleasure to be here. I'm sad that I missed the first round of Column, and I'm happy to be at the second one. And so many friends organizing, and so I'm very appreciative to be invited and really excited to see all the talks this week. To kick it off, I want to talk about our recent work on multimodal, or what I'll call mixed modal. I'll define that for you in a second. And I'll cover a series of different projects that really were very large collaborative team efforts. And so I can't possibly sort of thank everybody in advance that helped contribute, but I want to highlight some of the folks here that really led the projects. There'll be many more names at the end I'll show you. And in particular, I even stole most of these slides from them. But any places where there's problems, that's how I mashed it up, not anything that they did wrong. Okay, so the goal of this talk is to somehow figure out how to make a single, simple architecture that can language model all modalities. Okay? And I'll talk about what that means, why we might want to do that. This has been work we've been doing over the last 2 years, and the field is moving fast. So some of the ideas here are already, we use them every day, and we'll talk about what that means and sort of where we go from here. Although, we eventually want to do all modalities, actually we'll mostly just focus on images and text for now, but a lot of the ideas will really generalize. So thinking about what that means, this is a particular output that was generated from the Chameleon model, which we did about a little over a year ago. The idea here is that it's a full multimodal document. So rather than just generating text, like a lot of language models would, it can interleave. It can do this so-called mixed modal generation. And when it decides, it can switch into image generation mode and generate an image, switch back to text, go forth, and so forth and so on. And the idea is that as our models become more powerful and more general, we should just be in this mixed modal mode by default. Everything should just be one unified model. That was at least the hypothesis going into the work. Towards the end of the talk, I'll show you, it's actually a little bit more nuanced. It's actually not exactly clear how we should build these models, and we're still figuring it out. But again, why would we do this? Well, if you're using any modern sort of API to Gemini or GPT or any of the other services, of course they do this already. But when we started this work, that was not the case. It can hopefully give us a lot better visual reasoning. And I'll come back and talk about this a little bit later, but this is just some pictures from a sketchpad that I'll come back and talk about the kinds of thinking by drawing, other sorts of reasoning patterns. And of course, you can integrate across the kinds of textual reasoning and multi-step reasoning we know so well, and really integrate it into visual generation and lots of other problems. But now in general, not to put too much shade on others, but the world has kind of closed up a little bit. So I want to do this kind of architecture work, and I want to enable this reasoning, but I want to, as much as possible, participate in the open community and share it with others. And so, for example, Gemini is doing this too, but until recently, people sort of stopped talking about how their models work. We sort of have to guess. And this was from the Gemini paper, and it was the last kind of architecture figure, I think. And even here, it's clear we're going multimodal, but there's not a lot of detail. Okay? And so I would like to be able to share as much detail as we can. We'll see over time how these trends come and go, how they change, but how do we sort of develop these architectures and try to figure out what will scale, even though we're not at the most gigantic scale, because once you get there, you sort of stop sharing, unfortunately. That's the way the world works these days. A little bit of background to help us develop these joint text and image models. So there's I'm sure folks all know this, but I just want to review it to have the terminology that I'm using in place. There's kind of two different ways to do image generation. You can do token-based or diffusion-based. And it will become important as we think about how to integrate with text to really be careful about which version we're doing. And I'll try to remember to remind you at each point which version we're in. But for lack of so DALL-E 1 was token-based, DALL-E 2 became diffusion, and lots of models that just generate images are often diffusion-based. Other models like Party and others that have really scaled up show that actually token-based can also work, really, really well. And it's an interesting trade-off between the two in general. So just to make that a little bit more precise, when I say token-based or discrete image tokenization, what I'm talking about is pre-training an autoencoder that takes an image as an input, maps it through this first little box on the left there, into a sequence of discrete tokens, maybe a vocabulary of around 2,000, maybe 1,000 to 4,000 of those tokens for each image, and then another little gray box that can map those tokens back to an image. And these little gray sort of polygons here, these are pre-trained. You're gonna do this as an autoencoder, you're gonna go through a whole bunch of images, and you're gonna figure out how to do this mapping, and then all the modeling and architecture work I'll talk about later in the talk is gonna assume this is pre-trained and fixed and available to you, okay? So that's what I would call discrete tokenization. But then the flip side, and this is, if you do that, then you're sort of working in the space that looks a lot like text, and I'll come back and talk about that more as we go. On the flip side, you can also then, more recent models have looked at things called continuous tokenization, and it's sort of confusing that these are also called tokens, but it's basically the exact same setup. But the difference is that the tokens are, an R to the n, they're vectors, and they're again trained end to end, but you don't ever have a discrete component, and in practice, you tend to have quite a lot fewer tokens for these kind of methods. You don't need so many to get good results. Okay, so I apologize, a little bit of boring background. Let's launch into the actual research with that in mind. I'm gonna do 4 different things. One is a little bit of an extended motivation for the whole line of work, talking about a particular type of visual reasoning, and then 3 different architectures that build on top of each other. One that's token-based, one that's continuous, and one that actually looks at sparsity and sort of more efficient learning, and then I'll end with some thoughts about future work. So for the visual sketchpad, this is really to motivate this whole enterprise and show some cool things you can do with it. And I want to especially highlight Weizhou and Yushi that led this project and really deserve all the credit for the work. So what do I mean by visual reasoning here? I mean, you could think there's so many different instances of this, but imagine just a simple geometry problem. So given particular angles in this drawing, find some other angle. And you can feed this into your favorite model, not to beat up on any particular model. Sometimes they'll get it right, sometimes they won't. But sort of natively in the model, just by doing generation, they don't always get the right reasoning patterns you want. If a person were gonna solve this problem, what they might do is actually just go and draw a line and sort of draw some extra triangles, think about some extra angles, figure out how to do the reasoning, but do the reasoning sort of in the visual space as opposed to in the textual space, okay? And more generally, I think that's kind of a mode of operation for reasoning that we could imagine trying to get models to be able to do. So can models kind of sketch their ideas? Can they reason visually? Can they interleave that with text in interesting ways and draw much better inferences than they would if they couldn't do that type of reasoning? We did an early version of this, maybe about, it was in NeurIPS last year, where we said, like, actually, yeah, they can do this, do it really well, and in particular, if you just kind of augment it with tools. So the idea is if you want the model to be able to draw that line, just ask it to write some code to draw that line, create the corresponding image, and then feed that image back into the model and iterate and so forth. And that actually works really well. You can not only use plotting libraries and draw lines for geometry, but you can do this very, very generally. So you can do it, for example, you can use depth maps as a tool. You could use object detection as a tool. You could use segmentation as a tool. Basically, all the different visual reasoning or drawing and other things you might want the model to be able to do, you can just provide those as tools, and it'll be able to do it. It'll be able to look at the outputs. It'll be able to do much more interesting reasoning on top of it. All right. So let me walk you through a quick extended example, show you a little bit of figures, and then a little bit of results, and then you'll sort of get a flavor, but you'll really have to look at the paper for the full details. So if I showed you this image, and there's these 2 little dots here, A and B. They're kind of hard to see, but they're just sort of random pixels in the image. And I asked you, which point is closer to the camera, A or B? You'd have to think a little bit. You're not really sure. But if you were one of these reasoning models, you could go into your text mode. You could think a bit, and you say, well, you're asking me about a distance estimation problem. Why don't I run the depth map tool? You call some code to do that. You get that image. You feed it back in. And then the model can think a little more and think about what the colors mean in the depth map, how to interpret them, think about how to call various overlay functions, look at different colors of different pixels, and finally figure out sort of whether it's which point it is. Okay? So that's the general pattern. That's what we would call a visual reasoning chain in this work. And again, for the exact set of tools and the exact set of patterns, I encourage you to go look at the paper. But it works very generally for a wide variety of different tasks, both kind of sort of geometry style and other reasoning tasks, as well as various vision tasks. And when you do these math tasks, you get some nice bumps in performance. I'll go very quickly through the results, but you can compare to a base with and without this extra tool augmentation or sketchpad, both for these kind of math and also for visual reasoning tasks, and it works quite well. Now, the world is sort of insane. Things are moving at a breakneck pace, as I'm sure we're all feeling in this room. And so we did this work, I think, like about a year ago, and even just a few months ago, it's already very similar ideas. I couldn't say the exact causality of these ideas, but very similar ideas are already showing up, like in the chat API models. So the OpenAI 0304 thinking with images was sort of a cropping tool that's kind of an instance of this kind of visual tool used for reasoning. Okay. So more generally now, that's kind of our extended motivation. Like, we want these very general models. We want them to be able to handle any architecture. And so the rest of the talk is really going to focus on architectures for doing that. And you could think of this as kind of dually motivated. Like, these would be the models you would need to call the tools if you wanted to directly apply sketchpad. But also, maybe eventually we can get this reasoning to be more native and less in the tool space. And what would it take to get a model that's powerful enough to do that? What would be the trade-offs? I'm not going to answer that question, but that's sort of interesting to think about and the kind of future direction we'd like to go in. All right. So the first approach, and this is the older models, is think back to my two tokenizers. Think if you have a discrete tokenizer. So every place you have an image, what you can do is run that little pre-trained gray polygon, your encoder, and every place in your data that you have an image, you just replace it with 1,000 discrete tokens. So you have to go out and gather data that's interleaved sequences of text and images. You do this pre-processing step on your images, and now when I look at my data, all I see is text. Right? So the column conference, we should be very comfortable in this world. And I can say everything is discrete tokens. I'm just going to train exactly as I would if I were a text-only model, and I'll be able to do multimodal. Okay? And so this was about a 2-year research enterprise that we did. And we literally, the sort of goal was to just kind of copy the GPT scaling recipe and apply it in this setting. And write papers and be open and talk about what we did. So you can do normal transformer causal pre-training. You can do all your favorite alignment tricks. We mostly stopped at fine-tuning, but all the RLHF and fancier alignment techniques, of course, would work. You can even do things like retrieval augmentation and so forth. And so I'm going to take you through this very quickly, kind of just little vignettes about all these different steps. We have various papers you can look at. And then I'll spend most of my time in this section of the talk talking about trying to scale an approach like this up. So what would it get to, how would you get it to work for sort of 30B plus parameters? How would you get it to scale? And it turned out to be trickier than we thought. And I'll just give you some discussion of that. All right, so just to recap, or to sort of be a little bit more detail, when you train a model like this, again, it's really exactly a copy. So we literally, this was a project that was trained at Meta, and we literally used the exact same code base used to train the Llama models. Okay, so you just pre-process your data, you train it, you have a transformer. At inference time, actually, no big deal. Actually, you just you run that transformer and get your sequence of discrete tokens. It turns out anytime it does image tokens, it's always right. In this case, it was 1,000 tokens per image. It always knows exactly to do 1,000. It's very simple, easy for the model. And then you just have to run this one little extra polygon that I showed you earlier to take those discrete tokens after they're done, put them back into pixel space, and now you can do interleave generation. Okay? So super, super simple setup. Now, what we wanted to do is think about, how do we scale this? Okay, so we put basically about a year's worth of work into preparing for that. We did all of our scaling laws. So I won't encourage you to go look at the paper. I just have one slide vignette here. This was actually more than just image and text, but for the purpose of this talk, I won't go through it all. There was some speech and other things. And you get nice scaling laws, and you have to add a few extra factors for modality-specific kind of power law components, but you get good behavior, and we think we're getting a pretty good idea of how to set the hyperparameters. We also did just a little bit of post-training. We did sort of the massively multitask kind of version, and we sort of showed that, of course, the model can generalize and do basically all sorts of different visual input and output, visual and text inputs and outputs. This was a little while ago, so the images I'll show you later in the talk will be much more beautiful, but you could control with all kinds of different things. So you could prompt with images to get it to match the style or the pose or other things, in addition to prompting with text. And then just for fun, if you're interested, you can also do retrieval augmentation. So very sort of long-tail visual concepts like particular vases or particular styles of architecture. If you prompt for those, it can actually retrieve images that show that, condition on those, and do a much better job of actually using that long-tail knowledge to generate the right images. But given my limited time today, I really want to think about sort of the more architectural issues, and in particular, kind of figuring out how to scale these models. Again, I'm just giving you a little bit of exposure. I can't take you through all the details. But we designed a set of experiments to go up to about 10 trillion tokens. So this is our balance of tokens. These are our model sizes. This work was done in parallel to Llama 3, so we kind of borrowed the Llama 2 setup, and we sort of said, we just want to clone this directly. So how do these things that we know are working for text actually scale on this mixed modal setting? Turns out, even though we had done our very careful scaling laws and tried as hard as we could, scaling is difficult and it's kind of messy, and we didn't, it was a lot harder than we thought. And so we spent a very painful summer trying to run 7B models over and over again, and getting them up to running them for weeks on a very large number of GPUs, and then having them kind of slowly diverge, and all kinds of other crazy things happen as we went. Eventually, we were able to stabilize it, so now some of these tricks like KQ norms and dropout and Z-loss and so forth, these are kind of standard. People use them all over the place. I will say in the multimodal setting, it was actually harder in the text-only setting. We don't perfectly understand why, but probably because the image tokens, the text tokens, they were just in the model altogether in one softmax, and they're distinct parts of the data, and so they were kind of competing with each other and sort of fighting back and forth, and you were getting weird things with the norms growing and stuff like that. I could give a whole hour talk about that, and I still don't think I would understand it, so I just give you a little glimpse and encourage you to go look at the paper for an imperfect but some idea of what was going on. Okay, and then once we got everything stabilized and training at the 7B scale, we went up to the 34B scale, and again, the recipe didn't work. You have to keep working on it, and in this case, we added a particular extra norm, and finally, we were able to stabilize and train really well. Okay. I will kind of leave out the details, but encourage you to go look at the paper for the final recipe. I don't know what would happen if we tried to scale again. Like, these things work. Undoubtedly, there are many companies with these types of models in production now, much bigger than this, and so there are almost certainly recipes that are hidden, that are not shared with the world for getting the scale even further. But it's kind of interesting and sort of, it will work, but it's not as easy as you think to just scale up, as people often say. Lots and lots of different evaluation in the paper. I will just quickly say that, when you're doing this full mixed modal setting, it's actually not so obvious. Like a lot of your standard benchmarks that we focus on in the world are sort of multiple choice or other things. So we've made a bunch of prompts here that have mixtures of text and image in them, or require outputs that are mixtures of text and image. Evaluated performance across those, comparing to various different baselines. And we're able to find, the model is pretty competitive at the scales that we were at versus other sort of vaguely, these baselines here are mostly sort of hybrid tool use models, because not a lot of models at the time could actually do that sort of hybrid, the full reasoning. Okay, so that's our baseline architecture, and I'm going to build on this as we go forward to introduce more architectures that integrate more continuous things. But what we see well is that, actually, this discretize everything, tokenize everything approach actually does work quite well. You can get it to scale. Maybe others can do it more smoothly, but for us it was some effort, and we'll see where it all goes going forward. More recently, after we did this work, others, of course, have continued to push this kind of approach. So there's this really nice EMU3 paper that showed if you scale up. So we were using about 1,000 tokens per image. If you scale up to something like 4,000 tokens per image and really put in a lot of compute, a really careful data work, of course, and some amazing research here, you can get it to scale even more, get beautiful images, even get it to do video and other things. And who knows exactly how the OpenAI models work? They're not going to tell you, but rumor has it that some of the GPT-4o type models are token-based. And they've obviously got it to work very, very well. But more generally, from a research perspective, I think in the end, when you do this discretization, as you use more and more discrete tokens, you'll get better and better approximations to the image, but you will always have some irrecoverable loss, right? It is, in the end, a quantization problem, and you won't be able to perfectly represent things. And so, we sort of measured that in various settings, but then we kind of stepped back and said, okay, we understand this sort of architecture reasonably well, and could we do better? So could we figure out things that are sort of equally native integration of text and images, but actually maybe have less of this irrecoverable loss, maybe more efficient, so forth and so on. And that led us to think about these transfusion style models. And in transfusion, what we're going to think about is how do you do a hybrid of sort of classical text language models and diffusion models, which were sort of now established in parallel at the time as being sort of a much more efficient way of doing image generation. And the idea here is actually, again, like I said in the very first slide, let's try to keep things as simple as possible and only add complexity as we go. So this absolutely adds some complexity. It's not just the same llama architecture for everything, but we're going to try to do it in the simplest way possible. So what I'm showing you in this picture here is that there's this single transformer backbone. You have image patches and text tokens, and that actually, what's going to happen here for the image patches is we're going to use those continual vectors. So again, think back to that beginning slide. We're in the bottom half of the slide now. We have our tokenizer, but it produces vectors. And we're going to say, OK, we're just going to have a single transformer that we're going to multitask train to be able to do both diffusion and normal autoregressive loss. And that's why it's called transfusion. So, if you don't have as much experience training diffusion models, the way the data is usually set up is you just kind of noise your images and you train a single denoising step for each example, different points in the diffusion process. So you can do this kind of hybrid training really quite straightforward. It's just that here, instead of these being tokens, they're image patches, but it doesn't matter because transformers, of course, take vectors at the bottom. And then you just kind of noise those patches, you feed everything through, you have a different loss for these tokens than you have for these tokens, but it's fine. And so to think about the transfusion approach, it's very, very simple. Just multitask train a single transformer with two different losses on the different tokens. Okay? Once you have such a model, how do you actually use it? When you basically end up with a mode switching model. So it has two different modes that it can generate in. It can either generate token by token, this text mode, or when it hits a beginning of image token, it fundamentally switches mode. You lay out the patches for the lay out all the sort of initial noise embeddings for the image patches like you do in diffusion, and then you iterate n times through your diffusion process. But crucially, each iteration of that diffusion gets to attend back to all the previous tokens, including text, including previous images, and so forth. And then you can switch back and forth between those modes and do your full generation. Okay? So that was our, I'm sure you could do better, but that was our approximation to the simplest hybrid we could think of. In the paper, there are a bunch of different experiments and ablations. I want to highlight just one or two to give you some flavor of what's going on here. So again, for this transformer block, we're going to try to just copy something that we know that works. So again, we'll keep that a llama architecture. We'll literally copy exactly the same architecture that you would have used for a text-only model or for the Chameleon-only model. But then we need to take these are these gray blocks that do the tokenization and detokenization, and we need to project them into that space. And so one little place you get to do a little bit of architecture innovation is thinking about the right way to do that projection from the tokenizer into the transformer space and back out. And we played around with different things, just linear transformations, U-nets, which you could think of, if you're not a vision person, as like a sort of very nice, parameter-efficient sort of convolution version that can do projections like this that are very commonly used in vision. And we can do different ablations. We can try out all of our different hyperparameters in this setting. You don't need to look at all the details here other than to say we did a fairly exhaustive study of like how many patches you would need, how you should project, all the different sizes, how to hook them up. You can look at the paper for the full details. And really nice result here is that we could actually get images down to about 16 patches without losing a lot of performance. You get pretty good performance on only 16 patches. Contrast that with what I was just showing you in the last section. We need something like 1,000 or 4,000 tokens. So it's a shocking multiplier, right? Like 16, you'd much rather use 16 than 4,000. Okay, so it's a big efficiency difference here. And then the other interesting architecture, the sort of architecture change to point out is this kind of block autoregressive nature of the generation. So of course, when you're in the text-only mode, you're going left to right like this. But when you go into the image mode, because you're doing that iterative approach, you actually have this nice off-diagonal block, where as you're doing image generation, you get to look all around. You don't have to do image generation left to right. So the paper, again, has a bunch of ablations about that, and it really matters a lot. So if you were to do a version of this where you just did everything causal, you didn't have this little extra block here, your performance is much, much worse for lots of different tasks. So image generation really does, it's much easier if you don't have to plan it all left to right, which is intuitive and nice to see in practice. Okay, now finally, we did some scaling. We didn't go quite as big as in the last version, but we run a bunch of different experiments, and this is sort of head-to-head, very carefully controlled data, compute, and everything, comparing transfusion to Chameleon, and it's just much better all around. So again, I won't take you through all the different numbers here, but you're seeing sort of large multipliers in performance, and not too surprising given what I was telling you about the number of tokens and so forth, but really nice to see it holding up in the experiments. Now I get some slightly more beautiful images. I do have to say, as an aside, that I'm a lifelong text-only person, and so it just brings me joy to put images up on slides. I just think it's really fun to kind of show you this. And now I'm actually getting ones that are kind of nice. But you sort of, the model is, these are far from state of the art, but you're starting to get pretty reasonable models at not too insane of compute budgets, although far beyond academic. Okay, so in summary, for transfusion, we're combining language modeling with diffusion in a single transformer over these mixed modal sequences. And we're getting sort of, I think, I didn't mention it, but the training is also much more stable. All those issues we had with the Z loss and so forth largely go away. More efficient, more stable, better training overall. And then again, this is me just wildly speculating, but some of the API models out there almost certainly are richer hybrids of diffusion and text models. And the way you would know is if they're able to keep better pixel level sort of consistency across the images. Like if you try GPT-4, often the faces won't be quite the same as you go through a sequence of images. So, the Google people can't answer this, but I would speculate that they probably have a much better way of doing this than the OpenAI people. And who knows if that's true or not. But you see this kind of nice consistency across the images of a generation I did last night in their API. Okay. But where do we go from here? I have a third architecture I also want to tell you about. And to motivate that is going to be relatively quick, but to motivate that, the whole point here was that we would really like to do a joint model. And so if you have a joint model and it's working well, and you sort of look into the embedding spaces that it learns, what you'd like to see is across the different modalities, really nice alignment, like things lining up. You're getting cool transfer, the visual concepts and the text concepts are kind of sharing, they're overlapping, interesting things are happening. And I think this is a visualization for Chameleon. It's also true for transfusion, it's true for all the different models we tried. But if you sort of do various layers, various representations, you start looking at different modalities and embedding them together, actually, unfortunately, we don't see this happening in practice. So we see in the, this is very, very qualitative and post hoc, but we see that the embeddings sort of separate by modality. And that's what you're seeing with these different distinct color groups. And in practice, actually, you have to wonder, how much are we actually benefiting from having a joint model across the different modalities? Or how much are they sort of internally fighting with each other with their learned representations? And I think this is getting, this is my sort of 2-year story arc. We're getting closer to sort of right now, and it's not entirely clear. So we have some ideas. I'll show you a new architecture that plays with this idea, and we actually are going to get efficiency by not sharing the representation space across the different modalities, which is sort of disappointing, but also maybe just the way the world works, but also kind of an open science question to really understand. I don't think we've resolved this fully. Okay, so this last architecture is now a mixture of transformers architecture. What are we going to do here? I just have a one-slide vignette kind of showing you this. It's exactly the transfusion architecture I showed you before, so it's exactly the same. But now what we're going to do, think of this as very similar to a mixture of experts, but we have different parameters for different modality. And the parameters aren't just the feed forward, it's the entire transformer. Okay? So if you put in an image, the set of transformer parameters are going to be different that you use than if you put in, say, speech, or you put in text or some other modality. Okay, so this feels a little bit circular. We have a different model for each modality. But crucially, these models, say you're doing a forward pass on a mixed modal document, they're all running in parallel with each other, and they're all fully cross-attending to each other. So it's very much one model. It's all jointly trained. All those parameters get to interact with each other during training and inference. But you get different capacity for different modalities, and there's no hard routing problem like in MOE. It's just a very simple deterministic routing problem because you know exactly what modality you're in. Okay? And what we did is we did a whole bunch of experiments with these so-called mixtures of transformer architectures. And across lots of different architectures, Chameleon and Transfusion in particular, different modalities, doing this so-called mixture of transformers approach is just much, much better. So you can get things like 3 times more efficient flops and so forth and so on. Okay? I don't know how I feel about this, to be honest. Like, there's sort of pluses and minuses, but more efficient is good, even though the models aren't behaving the way I expected in the beginning. Looking a little bit more closely here, this is training steps. This is sort of trying to match dense performance. This is just the training loss. This is for an image and text only setup. So when we look at this case, the text kind of matches the close to optimal text baseline, but actually the images get a huge gain from doing this. And so it seems what happened is, because the architectures probably were optimized for text in the beginning, we just kept sort of stealing that llama setup. The text was dominating, and the images were kind of fighting and having trouble keeping up. But if you break the images off and give them their own representation space, but of course they can all, communicate during training, they can all talk to each other, you can get much, much more efficient image training. Here are some results. Looking at this is a single dense model. This is the transfusion model versus this mixture of transformers model. You can see these different, somewhat more complex prompts. This is text to image only. And this is at like a finite point in training. So we've kind of matched the amount of flops that we're giving everybody. And in particular, these image generation to this sort of cute hamburger sitting on the couch is a bit more, in general, it's all just kind of a little bit what you would think of as kind of further along in training. Like it's where you would expect to be if you had spent more compute. It's looking a little bit better than we'd expect for the amount of compute that we put into it. Okay, this kind of approach also allows you to think a little bit more generally about how to do this type of training. So in particular, now that we've separated out the different modalities into their own transformers, you can start playing with different architectures for different modalities. So you can change around how things are set up. So in this slide, I'm showing you heterogeneous scaling. So in general, you can think like, a text model, you can take that thing up to 400 billion parameters, it's going to do better. But an image diffusion model, it just doesn't need to be that big. Right, so maybe we can allow some models to be bigger, some models to be smaller, but we can put them together in this mixture of transformers. We do that in this case by having the transformer for text is an MOE, which itself kind of scales up a bit, even though the input and output dimensions are the same. And then it works quite well. So you can say, you can look at heterogeneous scaling, you can look at giving the right amount of capacity to the right amount of architecture, and I'll let you look at the paper for more details, but that all works really well. And another really fun thing you can do is you can sort of, again, in that mixture of transformers, freeze some parts and train others. So for example, in this LM Fusion paper, Weijia and Han and others showed that you can just, well, why do we keep retraining the text part over and over again? We have such great text models. Why don't we just freeze one of the components in that mixture to be a frozen llama, and you train kind of the image component on top of it? Can you get more efficient training by doing that? And of course, you absolutely can. It works really well. And again, look at the papers for details. But now I get to show you, even more of these beautiful images that I love, you using fewer and fewer flops every time to get to these performance levels. Okay? All right. So I've been blazing through my slides, but that's okay. We'll have lots of time for questions. The summary for this third architecture component is, we can get these nice efficiency gains by thinking about actually separating out the modalities, modality-specific sort of scaling and other behavior, and this seems to be a better approach, although we'll see what happens going forward. And not too long after we put out this paper, probably they also independently discovered it, but there was a follow-up work, Bagel from ByteDance, doing very, very similar, effectively the same thing, but a much larger scale on better data. They had some really cool setup here, and they get really, really nice results. And this is actually an open model that you can go and play with. We've been using it in our research ourselves, and it works really, really quite well. Okay, so where are we at? I think that we've sort of seen this motivation, we've seen this whole series of architectures, and I think, I don't know the best way to do things. This is an open research agenda, but I think there are some pretty exciting directions to take this stuff going forward. One that we're actively working on right now is thinking about what would transfusion look like for video. So if you think about hybrids of autoregression and diffusion, video is a natural example. Right now, models sort of view the video as one big long frame, but wouldn't you rather kind of autoaggressively think about how to mix back and forth and do that kind of generation? There are, of course, some papers doing things like this already in the vision community, but I think there's still a lot more work to think about doing it with sort of richer prompts and interleaving of different types. I'm very excited to keep pushing on this heterogeneous mixture of experts scaling direction. How do you actually think about the right capacity and the right scale for things that's modality specific, but still having, joint end-to-end training with everything attending to everything and getting the best possible architecture for that, I think is really, really interesting. And then finally, I'm very, very excited about kind of the new types of architectures we can build on top of these methods. So, why is it that everything is autoregressive? On the text-only side, these non-autoregressive diffusion models and flow models have really taken off. What would it look like to do those kind of models in this setting? And we have a very recent paper that just came on arXiv, I think, yesterday. That's sort of doing a first version of that John and Ricky have been driving. And the idea here is that as you do your diffusion or flow process, you alternate between inserting tokens and denoising images kind of in parallel. And so as you're getting better descriptions, you're also driving the denoising and so forth. I didn't, this literally was very, very recent, so I didn't have time to put a full integration, but you should have a look. It's really quite interesting and quite fun. So in summary, the talk was mostly about these three architectures where we had this motivation of trying to do this richer visual reasoning. And we sort of showed that probably continuous is better than token, or maybe not, better is not the right word. I think you can get them both to work, but there's some interesting efficiency gains and other trade-offs. But that really, we haven't really figured out how to integrate everything properly yet, in my opinion. And probably there's sort of more back and forth. Like maybe where we'll end up is some sort of MOT type thing where some parts are shared and some parts aren't. Maybe you have some capacity that's in a joint space, maybe some that's not. We'll figure it out as we go. It's not entirely clear, but I'm excited to try to work on it. And I'll just give you a little flash here of some of the papers that I covered in the talk, if you're interested in following up. And I wish there's so many authors here and so many contributions, and I want to especially thank them for making all this possible. And I'm happy to stop here and take questions.
Check. So we have a lot of time for questions, about 20 minutes. If you have a question, please come to either side of the auditorium. There are 2 microphones, and state your name. Thank you.
Hi, Greg Durrett here. Thanks, Luke, for the really nice talk. I was really interested when you showed the modality separation, and it strikes me that for a concept like democracy or something like that, it makes sense to me that there would be no real visual analog. But what if you zoom in on something like a picture of text and how that's embedded by the model? Or if you have a word that has a particularly kind of painterly grounding or something like that. Do you have a sense of how it would look there?
Yeah, I don't have a perfect answer, but I share the exact same intuition. I mean, for example, the word apple, you would hope would be like embedded near pictures of apples. I think that my intuition, and I don't have great experiments to back this up, but my intuition is that there's just not enough of that. Like if you look at the totality of things across the different modalities, like some of that probably is happening, but that you get more of a benefit by not competing during training in the sort of parameter space than you do by getting the advantage of that. And I think that's a place where we could do better. Like some sort of hybrid approach that does some of both could probably even be better.
Makes sense. Thanks.
Yeah, thanks.
Mark.
Mark Steedman, University of Edinburgh. Nice talk, Luke.
Thanks, Mark.
There seems to be a huge difference between what you're calling tokens across the modalities. That in one modality, you've got words and sequences of words that have a semantics in the world. And in the other modality, you've got patches and not even a very clear sequencing relation between those patches. Are you going to do anything about that? I mean, that seems a crippling difference.
Yeah, no, absolutely. It's a great question. I would love to. I don't know how to. You know, you could imagine trying to make the models kind of more at the object, maybe object and attribute level. Honestly, both on the text side and the image side, although I think it's more glaring on the image side. I mean, we miss the good old days when semantics was all the rage, right? But I don't know how to do it. I would love to think about that. I mean, it is clear that internally in the transformer and all of its layers, there is some messy representation of that because, you know, it can do compositional things to a limit, to some, you know, reasonable degree. So then the research question becomes like, is it better to have that latent or is it better to push it into the input? If you push it into the input, you know, where does that, you know, in the end, we get pixels and bits in, you know, where do those come from? And so, you know, maybe in the end what you'll have is some sort of, you know, it's not clear to me. But it would be much more satisfying personally if we could do it. But I don't know how to actually make it happen.
Thanks.
Yeah, it's a great question.
Hi, Luke. Thanks for the great talk. My name is Immanuel Schlag. I'm from the ETH Center. And you were talking about how these architectures, these different models were more flops efficient. But I was wondering, like, how is efficiency in practice when we're talking about going through the data as much data as possible, and so making sure that the models are well suited to the topology that we have and things like that. I would assume going to Chameleon and now even mixture of transformers that you're actually slower in the end if you look at wall time than not. Or maybe I'm wrong about that. Maybe you can comment a bit on the efficiency in this.
Yeah, great question. Could you clarify which do you think is stronger, is slower than which?
Sorry?
So when you say maybe you're actually slower or maybe you're seeing less data.
Yeah, I could imagine like the mixture of transformer might be a bit more tricky to train because you'd have to maybe
great.
split the modalities between, or you have to do Chameleon. Well, I'll let you answer.
Okay, great. Yeah, perfect. So using fewer tokens rather than more tokens, whether they're continuous or discrete, you know, fewer is going to be a huge win. Right? You're just going to pack more of your data into the same number of flops because your batch, you know, you just like image will take up less of your batch. So that's just like a straight win as long as you get good performance. You know, and the worry is that you won't get the representational capacity. For the mixture of transformers, when you go there, there's absolutely an overhead because, you know, you have n copies of the model now. So you have more parameters, and you've got to think about like how do you distribute that across GPUs, or how do you manage space on your single GPU? It's a solvable problem, but it's definitely engineering overhead. But the more positive way of thinking about that is like free sparsity. You know, like MOEs are all the rage, sparsity is helping, you're able to grow your model bigger, and here you don't even have to learn the router, it's just deterministic. So whether you think of that as a good, there's more engineering complexity, but you get to go bigger for essentially no cost if you can work out those engineering complexity. So.
All right, thank you.
Yeah, great question.
Next question on this side.
Hi, Ivan Titov from University of Edinburgh. Thank you very much, Luke. Great talk. I think my question relates a little bit to the previous one. So I was thinking about kind of connections of MIEs and a mixture of transformers, and also your work, I think also from your group in the past, where you predefined routers for transformers for certain domains. So basically, in both cases, you define somewhat specialized parameter sets for different problem. So I wanted to push you a little bit on this. Maybe you have some more ideas. Maybe we should have a bigger models, which submodels, which kind of learn adaptively which parts of the input they should process. Or maybe your perspective that we should predefine these separations, right? Because in a way you can, it's one extreme, right? But you can see learning models corresponding to certain domains, or certain types of reasoning, and so on.
Yeah, it's a great question, and I think that it gets towards this idea of wanting, really dynamic and adaptive compute. So you'd like to, at inference time, apply your flops to where things are hardest. And this talk didn't, we've done some research on those kinds of ideas. I don't think we're anywhere near solving it in other contexts, but this talk was really not, we didn't have any of that. But if you imagine that you had some way of doing adaptive compute, definitely, even within the text, some tokens are harder than others. Definitely in images also. How would you get all that to interact? I think it's a fascinating space. But here, we're just saying, like, we're thinking more about sharing or not sharing, and not so much the adaptive nature.
Thank you very much.
It would be super cool if someone figures that out. I think that's a very exciting direction.
Hey, Agent Choi, Stanford and NVIDIA. Really great talk. I just so much enjoyed the content. Beautiful work, especially how you combine different modalities. I really appreciate that you said something about like how hard it was to train Chameleon because the different modalities logic interfere with each other or compete with each other. I came away with this impression that you didn't complain as much for transfusion. Is it because it just trains easier?
Yeah, I forgot to say it at the appropriate slide. I tried to sneak it in at the end, but it is just much more stable and much easier to train. That's right.
And about that transfusion, my impression was that maybe in the version that you presented, it was one image and then text before and after, whereas the Gemini slide where you speculated that they may have done diffusion, it seemed like a sequence of images, and then toward the end you also mentioned the video generation case where there could be a sequence of images. So if you were to extend it to the sequence of images, how does that attention block work? Is it just causal across the previous text and images altogether, and do you envision any challenges in dealing with a very long sequence of images?
Yeah, okay, great question. So I apologize for the slides, I oversimplified things, but every model in this talk, it can take arbitrarily long intermixed sequences of image and text, because it's all just tokens. So you have 5 images, no problem. You have a sequence of images only, no problem. It's all just sequences of tokens. And the data, the hardest part actually there is the data. You need to actually find data like that. And so, I think a lot of the closed models have, there's probably huge teams of people doing nothing but that. But everything, these pictures just had one image just to fit on the slide. And it just doesn't matter. They're just sequences of tokens. Now I'm blanking though, there was something at the end.
Oh, so in those cases, how does attention block work? Is it just like attending to everything?
Yeah, so it's always just a transformer, and every single forward pass of the transformer has self-attention over every image. I'm sorry, every token, regardless of what image or regardless of what text it was. It's all just one simple attention mechanism.
One last thing, sorry. And then, so you said that the data preparation is important, which sort of alludes to that, like if you didn't have data with like very long image sequences, then what happens during inference time?
Yeah, okay, good. So we have not solved the long sequence problem, but others are. Some models are doing millions of tokens. Depending on how deeply they're going, that's an interesting question. But in particular, in our future work about wanting to move to video, like that's clearly going to be a problem, right? So these models out of the box could do very short videos, no problem. But like doing long ones well, that's going to be a hard research challenge. So I think we sort of lean on others. Again, these base models are just transformers, and everybody knows that there's a huge, beautiful, active research on long transformers, and we can just copy whatever they come up with. That's kind of our mindset.
Thank you so much.
Yeah.
Next question, please.
Hi, Luke. Lawrence from UCLA. I was just curious. I saw on your mixture of transformer slide, there was something about MOEs on there. I was wondering, did you ever look into the router? Were there certain experts that were specifically tailored towards, like, I guess, images, and others towards text?
Yeah, great question. And I think that we need to do a better job of this going forward. But in the current hybrid models that we have, it's kind of, you can think of it as like a hierarchical routing, where you first route by modality, and that's deterministic, unfortunately not learned. And then within each modality, you can do kind of a classic learned MOE routing if you want. So there is unfortunately no learned router that goes across modalities. It's just, sort of, that's your sort of vanilla way of scaling differently within each modality if you want. So this would be a cool place for future work. And maybe that would give you your hybrid where you're sometimes sharing across modalities and sometimes not sharing across modalities. This kind of thing that we probably could benefit from in the future, even though we're at the two extremes right now. That would be a really cool direction to try.
So on your slide, I saw there was one about MOE specifically. Was that just like transfusion MOEs, or was that anything?
Yeah, that was, I think this one, if we could put the slide back up, please. Yeah, so this is this hierarchical thing I think that I just said, where you first deterministically route by modality, and then within each modality, you have a whole transformer there, you can do whatever you want. So you can make that text-only modality be an MOE, you can make the image-only modality be some other MOE, you can do whatever you want, but it's still, unfortunately, not jointly routing across modalities yet. That's future work.
So that's the MOE 4x? Or?
Yeah.
Thank you so much.
Yeah, sorry that wasn't clear.
So I'll interrupt for a second. The presenters for the next session, it'll be great if you come to one of these front tables just to prepare. Andre.
Hi, this is Andre Martins from the University of Lisbon. I wanted to ask you about your perspective on the compression part. So you didn't talk much about compression, but you mentioned that you either represent the image with 1,000 tokens or 16 patches, right? But it looks to me that there is something missing here, which is the adaptiveness of this compression, especially if you go to video, but also with images. It's very different if you're doing OCR or if you are answering questions about the image. Do you agree that there is something missing here in this compression? What is your perspective?
Yeah, 100% agree that you should have adaptive compression. It would be super interesting. Thinking about the two different, sort of discrete tokens versus continuous tokens in images, it's actually, there are some really beautiful papers on doing adaptive discrete tokenization. And, if we hadn't have gone the transfusion route, that would have been my top candidate for pushing Chameleon, is make the discrete stuff adaptive and try to compress the number of tokens. And I think it works. Other people have made it work. That is a very viable direction. I don't know if you could get it to 16 though. So it would be an interesting trade-off. Adaptive for diffusion, there's also work, but I think that looks a little bit more hierarchical, where maybe you do some sort of, you change the number of patches or you do other things. Although diffusion in general is actually quite efficient, especially the more recent advances that we can just keep copying again. So I think in that setting, probably for video, you would need to worry about a lot more, but for single image, it may be a little bit less pressing. Maybe it's just kind of reasonable. Although who wouldn't want to save with something adaptive? So I absolutely think this is just a great direction.
Even the problem of what to compress is, like for example, you had an example in the visual sketchpads with the crop tool, right? So sometimes you don't know what information to pay attention to before actually
absolutely
getting.
Yeah, and ideally the compression would be context dependent. And so then you get into this issue of like, when you have a pre-trained tokenizer, is that possible? And that's really fascinating. I would love to do more work breaking that boundary too. So another drawback of all of this was that slide at the beginning where I had those gray polygons that were all pre-trained and fixed. I'd love to break that barrier. And adaptive would be a great place to do it, but it's very kind of gnarly to think about how to do that right.
Thank you.
Yeah.
Hi, my name is Rahul and I'm coming from the data background. So just wanted to ask, like, as we can see, like in the research, most of the papers, they do not deep dive into what's the data pre-processing step or some recommendation like how should we like pre-process the data, clean the data. Can you please give us some insight on what might be a recommendation across multiple modalities in terms of data processing or data itself?
Yeah, great question. I think that I wish we had more science around data. I think this would be a great place for folks to focus on. Data quality is everything, but I don't know that there's a perfect definition of what data quality is. I will say, on the text side, you want it to be sort of real text, and if an editor has edited it or something, like there's been some effort putting into making it high quality text that you would publish or something, that's one notion of quality that does seem to really matter. On the image side, you can imagine, like, is it a random snapshot, or is it, a professional photographer? These are sort of very vague kind of notions of quality. And then when you get into the mixed modal or interleave data, is there a relationship between the text and the image, and is that relationship correct? So is there this nice narrative? Is it describing what's actually going on? and finding data on the web that actually has that full mixed interactive quality on both sides, proper correspondence between them is actually quite tricky. So there's a lot of the data in that setting is at least partially synthetic, actually. You use a lot of captioning models and other things to build it.
Thank you.
Yeah.
Hi, Giuseppe Carinini from UBC and Amazon. I have a question about this, the fact that the different modalities, they are separated in the feature space. You showed us the motivation for looking for better architectures. So I was wondering if you see, as these architectures, they become more complex, these distribution of modalities in the feature space to become more overlapping or closer, and that, if that can be a test for how effective these are in making the integration more like.
Yeah, that's a wonderful question. We haven't got to that yet. I would love to explore it. Remember, with this mixture of transformers, though, they are just literally different embedding spaces now. And so if you think back to like the multilingual days when you would have different embeddings, you would try to, like word embeddings, you would try to like rotate them and align them and look for correspondences and stuff. Presumably you could do that kind of work here, but we haven't. And so we can't really, there's sort of not as easy to just kind of do a Tisney visualization or something. I mean, that's also post hoc, but there's no sort of obvious one step. You would have to really develop it a bit more and do a bit more of work to get into it. But it is absolutely possible that there could be interesting correspondences going on here, that by freeing it up, some concepts, maybe like Apple, there's just sort of transformation. They are actually aligned, but it's just less explicit. We haven't studied that kind of thing yet, but it could be possible.
Thank you.
Yeah.
Hi, great talk. I'm Stephanie from Berkeley. My question is, in the physical world, we have a lot of examples of biological models that can take in and generate lots of different modes interleaved. So I'm curious, either retrospectively or prospectively, whether you think this line of work can learn from the neuro or cognitive sciences, or if the differences are too great to learn anything from them.
Oh, that's a wonderful question. And I'm embarrassed as a researcher. I wish I knew more of that literature. But let me nonetheless speculate. Especially again, luckily this slide is up. If you look at the brain regions, for example, like visual cortex is a thing, right? And it's separate from audio cortex and other things. Of course, now when you have injuries, they can relearn. It's very complicated. But you could argue that if you took inspiration from the brain, something like this, where you actually have separate processing for modalities, and maybe you need another layer that merges it in interesting ways, and maybe you need explicit memory, maybe you need other things, but maybe that's actually a better direction. We found it empirically. We were not sort of motivated by that at all, but maybe it's better than just having all of our stuff doesn't merge really early and then feed through one part. It's not all uniform. So I don't know, but that's wild speculation. I don't really know much about that literature.
Yeah, makes sense. Thank you.
Yeah.
One last question, please.
Hey, Nanyang Valley Pen from UCLA. Very nice talk. You talk a lot about the scaling on the model size and then compute side. I wonder what's your take on the scaling on the data? That's like relevant to the Databricks question, but my question is more specific. I view the multimodal alignment data is a bottleneck. It's like much more rare than raw text or raw image, and especially I think there is this one outstanding paper at Column here saying VLM models ignore their visual perception, and that's our observation too, as well as actually I think in the chain of reasoning model, that's even worse, that problem. So I wonder whether you have any take on this, and also whether you have thoughts on how to scale up the aligned data. Yeah, I also remember this one, that the amount is much less in the text.
Sort of this number here is a little disappointing, I
Yeah.
would say. That's absolutely correct. I agree with you. I don't have an easy answer. We're actively doing a lot of research on synthetic data for that number in particular, and I totally agree with you. It would be helpful to have more there. I will say that you don't necessarily need these to be all balanced. Like you do get sort of, all the models trained, you get some benefit. Whatever you learn from images only can also transfer to this case, for example. So a lot like in the multilingual setting for text, you know, you see transfer and so forth. You do see that even in the MOT version, you see that happening. So, but it would, you know, roughly speaking, you know, I sort of vaguely believe in chinchilla optimal sort of ratios and overtraining models and so forth. And that's all very true in the multimodal setting, but it's just harder to get interleaved data. It's just really hard compared to text only or image only. So I agree. I don't have a solution. I hope some of these models are, I hope they're a little bit better than some of the VLM stuff we're seeing, but I can't promise it's true, and we should look at it. Yeah.
Thanks.
Thanks a lot. Unfortunately, we have to stop the Q&A here. I apologize. Thanks
I'll hang
a lot.
around later if anybody wants to grab me.
Yeah,
Thank you.
Yeah.